Hey there, welcome back to Short Text 3031. Today we're going to continue our discussion of eigenvectors and eigenvalues. So this is part 2. And remember from part 1 we had our definition, our defining equation of eigenvectors and eigenvalues. And so given a matrix A, which could be really any linear operator, but we're going to assume for now that is a matrix, we say that we have an eigenvector and an eigenvalue when we have a vector and a scalar that satisfy this equation. So typically the matrix will have several different eigenvalues that will satisfy this equation for certain corresponding eigenvectors v. And the crucial property that I emphasized last time is that the eigenvectors really have to be non-zero. You can always solve this problem by putting v equal to 0. That's not what we're interested in. We're interested in v solutions v that are non-zero. And that gives us the so-called secular equation, or sometimes called the characteristic equation. In fact, most of the time this is called the characteristic equation, which is that the determinant of a minus lambda 1 has to be equal to 0. That is what ensures that we can have solutions to this equation that are given by non-zero v's, non-zero vectors v. Now from this equation we extract the values of lambda that gives us the possibility of having such non-trivial solutions. This object here, the determinant of a minus lambda 1, is a polynomial, is a so-called characteristic polynomial. It's a polynomial in lambda, and setting that equal to 0 means that you have to find the roots of that polynomial. And by the fundamental theorem of algebra, we know that those roots exist always in the complex plane. So worst case scenario, those roots, those lambdas will be complex. So we cannot always guarantee that they might be real unless the matrix is Hermitian. So that's the case. So if A happens to be Hermitian, then lambda has to be real. But in general, we don't know. And so, but at least we're sure by that theorem that lambda is at least in the complex plane. We also mentioned last time that we have a case, a specific special types of matrices called normal matrices, and those are such that they commute with their dagger. Commute means this, that you can put one on the other side of the other. So a dagger A is equal to a dagger. So the fact that these two different products in the different order give you the same answer is also written like this, usually in quantum mechanics, that a dagger A commutator is 0. And so that is what constitutes then the property of normality. So that the matrix satisfies this property is said to be normal. And this is very important because we have this theorem. The fact that A is normal is equivalent to saying that there exists a unitary matrix U such that U dagger AU is a diagonal matrix made out of the eigenvalues of the matrix A. And moreover, this matrix U contains the eigenvectors as columns, and the fact that we have to have U dagger U equal to 1 means that these vectors are normalized, by the way. And so then we have all this information in U and in D of the eigenvectors and eigenvalues, and if the matrix, which is guaranteed if the matrix is normal. If the matrix is not normal, then we don't have this guaranteed, but there are other things that could happen that we'll discuss today. Now, usually this process of calculating the diagonal matrix, or finding the eigenvalues and so on, is generally referred to as matrix diagonalization. So that really means find the eigenvectors of the matrix, construct the matrix U, and calculate U dagger AU, which will give you the matrix D. Now, in reality, to calculate the eigenvectors, you first have to solve the characteristic equation and find the eigenvalues. And then you insert the eigenvalues here and you solve for the eigenvectors. So in reality, you never really do this in practice in this way. So you don't access the matrix D of diagonal elements that are the eigenvalues in this fashion. You really just calculate the eigenvalues separately. But this operation is what one might call matrix diagonalization. So transforming A into a diagonal form in this way by sandwiching between U and U dagger. Now, if you multiply by U on the left on both sides of the equation and U dagger on the right of this equation, then you obtain this identity, which is U dagger UA, U dagger is equal to U D U dagger. Now, U dagger is 1. Here, U dagger is 1 because U is unitary, because we're assuming that A is normal here. And so that tells us then that A is U D U dagger. And this expression for A, for a given matrix A normal, is what we call the spectral decomposition or spectral representation of the matrix, because D, this matrix D, is what we call contains the eigenvalues, and so it's what contains what we call the spectrum of the matrix A. The spectrum is simply the collection of all the eigenvalues of the matrix, and so this then this expression in terms of the eigenvectors in columns and the eigenvalues is what we call the spectral representation. If you enjoyed this video and the series of videos that we have on the channel, please like and subscribe. If you're looking for a tutor in physics and or math in English or in Spanish, you can contact me at shorttext331@gmail.com, or you can leave a comment in the comment section below and I will get back to you. Now, all this that we just saw is if the matrix is normal. So what if it is not normal? And we saw an example of that last time. Now, in general, if A is not normal, but we can somehow find that it has a complete set of eigenvectors, that is to say that we know that the eigenvectors form a basis, then we can still form a matrix like this, made out of the eigenvectors of the matrix in columns. And that matrix will have an inverse. It will be a V inverse. It will not be a V dagger, the inverse, but it will have an inverse because the set is complete, then we know that there is an inverse. And moreover, if we apply A to V, we know that it's V times the matrix, diagonal matrix of eigenvalues. And this is simply the definition of the eigenvectors written in more general form. And if we multiply by V inverse on both sides of this equation, then we have V inverse AV equals D. And so this is another way to accomplish then diagonalization of the matrix in the more general case where the matrix may not be normal, but if we know that it has a complete set of eigenvectors. In the same way as we did before, we can sandwiches between V and V inverse and then rewrite a spectral decomposition type of identity where A is V, D, V inverse. This type of transformation, sandwiching between a matrix and its inverse, is what we call a similarity transformation. And so what we can say is that if the matrix is not normal, but we know it has a complete set of eigenvectors, then we know that it will be similar to a diagonal matrix made out of the eigenvalues. So by a similarity transformation, we connect our matrix A to the diagonal matrix of eigenvalues. Matrices that are similar in this way to a diagonal matrix are said to be diagonalizable. So the set then of diagonalizable matrices is the set of matrices that may or may not be normal, but that have a complete set of eigenvectors such that we can perform this operation. Now, normal matrices then are a particular case of diagonalizable matrices. There are diagonalizable matrices that are not normal, and there are also non-diagonalizable square matrices, and those are called defective. Okay, so it may be that you have a matrix that is not normal and also does not have a complete set of eigenvectors, and those are what we call defective matrices. Now let's see an application of these similarity transformations. So I've spoken about an example that sort of looked like this in a previous video, calculating the exponential of a matrix. This is actually very useful for a variety of applications in mechanics and in quantum mechanics, usually connected to time evolution. And so let's look into this. So suppose we have a matrix and we're interested in calculating the exponential of the matrix. And if we write this matrix in terms of its spectral decomposition, then this will be the exponential of V D V inverse, or V inverse dV, depending on what you call V. So there will be an expression of this form. And now you might ask, how do we define the exponential of a matrix? Well, we define it by its power series, by its Taylor expansion around 0. And so then the first term is just 1, the second term is V dV inverse, the next term is 1 over 2 factorial V dV inverse squared, which I wrote as a product in this way, and so on and so forth, all the way to infinity. Now for each term in this series, we can do the following. We can say, first of all, this 1, we can write it as VV inverse, and so this expression now becomes very symmetric. Notice that I took V inverse V here and I canceled it, this V with V inverse, so we have D squared, and here we can do the same at every term. And so what you see right away is that each term has a V on the left and a V inverse on the right. We put this by hand. We turn this 1 into VV inverse. This one has a V on the left and V inverse on the right. This one definitely has a V on the left and a V inverse on the right, but we also simplified V inverse V here as just 1 and then multiplied D by D, so we have D squared, and so on and so forth. We continue that to infinity, and now we extract V to the left and V inverse to the right, and we notice that what we're left with in here is simply the exponential of the diagonal matrix, because it's 1 plus D squared over 2 factorial, and so on and so forth. That happens all the way to infinity for arbitrary order, and so what we have then is V exponential of the diagonal V inverse. So this is very, very useful. You see, what we accomplished is that we managed to express the exponential of the matrix, which could be very complicated, and given that we have this spectral decomposition, we then wrote it as the matrix V, the exponential of the diagonal, which is very easy because the exponential of the diagonal will simply give us the exponential of the diagonal elements inserted at each of the diagonal elements. So if you have diagonal elements d1, d2, d3, and so on, then the exponential of that is e to the d1 in that first element of the diagonal, e of the d to the d2 on the second element, and so on and so forth along the diagonal. So this is very easy to compute. In other words, it's just the exponential of the diagonal elements on the diagonal entries. And then we have the inverse on the other side. And so this then gives us access to an expression that perhaps we can work with. Moreover, this is true in general for any Taylor expansion. So really all we used here is that we have powers of the matrix along the way. And you can always play this game that I just played here and write that a function of a matrix is always equal to this matrix V, and then the function evaluated at the diagonal of eigenvalues, and then a V inverse on the right. Here's another application. The Schrödinger equation is an eigenvalue equation. So in the following sense, so here I wrote the Schrödinger equation for a single particle in one dimension. Actually, here it's not in one dimension, it could be in any dimension. But here's the operator, or here's our matrix if you want, is our linear operator. This is our wave function or our vector. And then here we have an eigenvalue, and here we have the eigenvector again. So what we have here then is an eigenvalue, eigenvector type of equation. So how do we solve this problem? Let's focus on a particular case. Then suppose now that we're really in 1D. And so this second derivative becomes the second derivative of the function. And then on the other side, we have 2me. M is usually the mass of the particle, which usually appears on the left-hand side, by the way. Here I put it on the right-hand side to simplify things a little bit, and to focus on the derivative as an operator. And then we have the energy. The energy is something we don't know. It's the eigenvalue that we want to find out, really. And so we have this problem. It's a second-order differential equation, and then we need boundary conditions for that. And so let's assume that we're in this one-dimensional potential well. This infinite to the right, infinite to the left, and then we have our particle living here in this box. So this is really a particle in a one-dimensional box, and there's no chance that the particle would go to the left of this, no chance to the right of L, and so the boundary conditions are that phi, or I should say psi here, psi of 0, psi of L is equal to 0. So it should vanish here, and it should vanish here. How do we solve this problem? Well, the solution to this differential equation is not too difficult to guess. So we need a function such that when you take two derivatives of it and we change the sign, we get a constant times the same function. And so functions that we know that do that kind of thing, that when you take two derivatives you get the same function back, are usually exponentials or trigonometric functions. And so we propose a solution based on that knowledge of this form. So we say it's some constant times the sine of kx plus another constant times the cosine of kx. Now, first of all, this constant sort of had to be there because this equation is linear. And so if I have a solution and multiply by a constant, or if I have two solutions and I form a linear combination, it's still going to be a solution, okay? Because we have this equation is linear. And so if these two are solutions, then the linear combination will be a solution as well. So this C1 and C2 have to be there. And this K that we inserted in here is what's going to help us account for this 2me. So let's see how that goes. If we take this solution now, and we take two derivatives, then we get k squared times the same function. Let's see how that works out. And actually before that, notice that this C2 has to be 0 because we know that the function has to vanish at the origin here at 0. And so this is naturally 0 at this point, but this is not. And so if we want the function to vanish at this point, then the only choice is that C2 is 0. So let's get rid of that term right away. And now we take two derivatives of this object. And if we take two derivatives of that, then you find that you pull out 2 powers of k, and then you flip the sign. And so if you do minus second derivative of x, of psi with respect to x, then you will get the same function with a minus sign. So this minus sign will cancel that sign, and you get 2 powers of k. So you get k squared times the same function. And so we're then in pretty good shape. So we need two derivatives, minus sign, two derivatives, minus sign, and we have 2me psi, and then k squared psi. And so, okay, well, very well. So then that means that k squared must be 2m times E times this energy. Moreover, we know from the boundary condition that the function has to vanish at L. Also, it must be that when I evaluate the sine of KL at this point, right, sine of KX at L, so sine of KL, that has to vanish. And the only way that can vanish is if I coincide with KL at the roots of the sign of the roots of the sign. And so this must be then the KL is n times pi, where n is equal to 1, 2, 3, and so on all the way to infinity. We do not want n equal to 0. If n were equal to 0, then the solution completely vanishes, and we don't want that. Remember, we want eigenvectors that don't vanish identically. Good. And so we have this KL equals n pi. This gives us the allowed values of k. So we put L on the other side of the equation, and that tells us what values of k are allowed in this proposed solution. And we see that they're quantized. We see they're quantized. And those are going to be our eigenvalues. They're going to tell us about our eigenvalues in this way. So if we calculate k squared, then we have what goes in here, which is 2me. Remember, k squared is 2me. And so k squared is n pi over L squared. And so that tells us that the energy eigenvalues that are allowed for a particle in this box are n pi over L quantity squared divided by 2m. So these are then the possible energies, and they're quantized, and they go like n squared. So the first one is for n equal to 1, then the next one for n equal to 2, and so on and so forth, and they go all the way to infinity. Those are the possible eigenvalues. So going back to our eigenvalue equation, then, or this is our eigenvalue equation, eigenvector equation, we did not use the determinant in this case to calculate the eigenvalues. We simply used the boundary conditions. And so we determine then the energies. And so our solution then, fully spelled out, looks like this. We have functions psi sub n, characterized by a particular index n, which are given by some constant, which I haven't determined, times the sine of k n times x, and x goes from 0 to L. This k is indexed by n. As I said before, the only values of k that are allowed are n pi divided by L, and so that's why I added index n. And so n goes from 1 to infinity, and the energies associated with those eigenvalues, or those values of n, are simply kn squared divided by 2m. And if this looks like p squared over 2m, it's because that's really what it is. This is simply a kinetic energy. If you were to plot these solutions, suppose we fix c to be a constant, then if you were to plot these solutions, it would sort of look like this. For n equals to 1, it would look like a dome, like this. For n equals to 2, it would look like this. For n equal to 3, it would have 2 nodes, and so on and so forth, all the way to infinity. And that's it. That's our example. Again, we solved an eigenvalue equation, eigenvector eigenvalue equation, which took the form of a differential equation, so we didn't really use determinants. We solved it in a different way, but this is a typical classic application of eigenvalues and eigenvectors in the context of quantum mechanics. That's all I have for you today. If you enjoyed this video, please like and subscribe. If you're looking for a tutor in physics or math, you can contact me at shorttext331@gmail.com, and you will find the notes for this video in the description. So I'll see you next time.